Starting it.
Yes, recording in
Yes.
progress.
Yes. Hi, everyone. This is Beril Kara. I am the communication coordinator of the Quantum Tech Society at Izmir Institute of Technology and the volunteer editor at the Physicabar website. Today, we are going to have an interview with the Doris Reiter, Professor Dr. Doris Reiter from the Technical University of Dortmund. Doris, welcome. How are you?
Hi, thank you for having me. I'm good. Thank you. It's exciting to be here.
Yes, I think so too. It is really exciting for me too. Doris, can you please introduce yourself for the people that they don't know you? I know you, of course, but some people.
I think you already heard my name. It's Doris Reiter, and I'm a professor at TU Dortmund University, where I have been now for 3.5 years. My field of physics is theoretical physics, so I'm sitting not in a lab, but I'm sitting most of the time in front of my computer, so doing simulations. Sometimes I actually use pen and paper nowadays, but it's become really rare because I'm leading a research group. It's a small research group of about 5 people at the moment, and they are doing also a lot of the work.
Yes.
More specialized, my research field is quantum optics, so I'm really interested in like simulating what's happening in the quantum technologies world, seeing how photons are generated, how photons are detected, and what we can still learn about that beyond technology.
Wow, it is really interesting. I'm not an expert on your area, but from the Contour project, I know something about that, and I was researching a lot for the Contour. What is the quantum dot light source, and what we are doing onto the laboratory experiment, and so on and so forth. They're going to talk about this kind of details. But firstly, I want to congratulate you about the Lice Meitner Medal and Prize.
Thank you so much.
Project team. You did a really great job. Really great job. Congratulations.
Thank you so much. We're really happy. Maybe I can talk a little bit about what the Quantum project is about. Maybe not everybody knows that as well.
Yes.
So, so Quantor is about sending a single quantum emitter around the globe. So we started off sending it through Europe in sort of a relay race, and then also mentioning coming to Turkey. It was now in Canada. It was in Singapore by now. At the moment, it's sitting in my place at home, and it was a really fascinating project. So what we did do is my colleague Tobias Heindl, he fabricated a semiconductor quantum dot in a nanophotonic structure. You can imagine that as an artificial atom, and this artificial atom gives you single photons. And at each stop we have, the labs were encouraged to measure these single photons to prove I have quantum light from this emitter. And everybody did, and it was really, really amazing, not only to see that the physics should be everywhere the same in the world, but also how people came together and really talked about the same thing and exchanged perspectives on what they're doing in their lab, how they are working, and just having a really good time together with the source.
Yes, I know. How can I say? I was following all of the steps of the contour. Let's say the 12 European countries, we know that. And then the Turkey has just came to the, how can I say, came to the project, and the Canada Waterloo, as I searched, and the Singapore and beyond that the thing. And it was a really fun journey to follow and to live.
I think it's quite interesting to see. Sometimes there's a prejudice against physicists that we're always sitting in front of our computer or in the lab, in particular in the darkness, because labs need to be dark if you want to do single photons. But in fact, physicists also have a very creative side. When we went to the Netherlands, someone crocheted little photon. You've seen that red little ball, which is inside the suitcase now. That was not giving birth. It was just joining the journey all along. When it was in Rome, we did this really cool movie where they like explored different parts of Rome. Sorry about that. And I really made a full 3-part movie out of it. And I think it was also great to see when we included Turkey, because there was this big challenge if Turkey would be interested in having the quantum source, and like the resonance to that was just amazing.
Yes, I know. The Easter Quantum Days was really crazy. I have the Instagram account of you, and I think 5,000 followers you have.
Yes, at the moment we have about 5,000 followers approximately, and I feel like most of it came with a challenge. And of course, if you have like something which runs as big on a social media platform, it multiplies immensely. So it was a really interesting experience. You might imagine, sorry, As a physicist, we're not so much exposed to social media at the moment, but I still think most of the young people, they are there, and it's good to reach them and see, like, creates a vision of physics is also fun. Physicists are fun, and also physicists are coming from all angles of the world and have very diverse backgrounds.
Yes. I think there are lots of, this is not the, I think this is a general truth. There are lots of people who are really interested in the quantum physics with the different eras. We can add some kind of a quantum to quantum optical era, like the quantor, quantum light source, or something else. It is a kind of a really big privilege to have you that kind of a project.
It was a very unique project because it was something very new in that most of outreach focuses on educating, but basically we just told the story physics is fun, physics is interesting, physics has to do with everybody, everyday life. And in particular, quantum physics is like will touch us all. We have all these technologies going on in quantum physics. Maybe in 10 years, um, quantum optics or really quantum technologies will be in all of our pockets like the smartphone. Nobody thought 70 years ago that we're going to have a smartphone all in our pocket and just like a living computer. So it's really exciting times to see where will we be in 10 or 20 years with all that technologies. And I feel people who would be interested, they can really go out, and there are so many resources where you can learn more about like the quantum physics. So this gap we didn't need to close, but we need to close the gaps that physics and physicists are really fun.
I'm really close to your thought about this. How can I say? There are lots of open sources to understand the quantum physical things and educating, how can I say, education
Yes.
programs like the MIT OCV or something others.
Yes.
But it is important to collaborate at that era. How can I say? It is important to do collaboratively with some kind of a project or some kind of, how can I say, with the research group or something else. It is really important to do that onto today's century. We call that the space century, and it's, how can I say, it is compulsory.
It is not like nowadays physics, you really work together. You work in teams locally, you work in teams globally, you need to exchange. We all go to conferences where we like discuss all sorts of recent progress, and this is what makes all the physics and technology so successful.
Mhm.
It's not the story of someone working alone in their lab. Oh, sorry.
It's okay.
uh, working alone in the lab, but people coming together and doing a collaborative project. Also in quantum physics. We know this from particle physics or high energy physics, where they have the large colliders, they work together.
Mhm.
And it's also a huge collaboration, and sometimes things that's like it, but also in other areas of physics, may it be quantum physics, may it be solid state physics or biophysics, people are collaborating. So that's actually a very collaborative bunch of physicists we have.
Yes, I think this is a very fun thing. Yes, it is really important to think alone, to create something, some thoughts maybe. And then we have to discuss some new things. We have to, well, how can I say, create a new ideas, and maybe we can
Yes.
found the, how can I say, answers from the unknown problems. It cannot be, but we have to try.
And you always get like the new ideas if someone asks you questions. So sometimes you don't even know what will spark the new idea. Sometimes it's a very, what people would say, simple question, but then it makes you think, oh, I haven't thought about this problem from that and that angle. And then it goes forward because from yourself, these questions come in part, but most of them come from other people.
Yes, I think so. This is very fun. I can say that as a physics student and you as the professor of the physics, it is really fun to talk and discuss everything about the physics. It doesn't matter what is the areas. This is my own perception. So maybe we can get into the other question. It is really related about the counter project too. I'm really wondering that. We said that at the first time we just started the counter project, there were the 12 European countries, and that the Turkey and the Canada and the Singapore, there are lots of countries that are contained to the project. But I wonder, how did it grow into one of the world's largest, greatest outreach projects? This is a very important question.
Uh, I feel it became so big because everybody joined in with their creative thoughts. We started off saying it when we designed the project, we thought about going around the world, and then there are some logistics problems. How do we go actually to Canada? Can we fly? Will the source be small enough to be taken onto an airplane or not? And Europe was like logistically, it's more easy to reach places because it's just closer. So we started off like having it European, and then we saw people are really like engaging, and then when we started it, we didn't know is this going to be a success or it's going to be a fail. Yeah, this is always you have an idea, you start it out, and then something will happen. I don't know what, and it just flew. And I think we did a couple of things in hindsight. You always know what were the things you did right. I think one thing was very crucial is we teamed up from the beginning with an outreach expert. So we had Pranoti Kshisaga, who's a science communication expert, and she taught us a lot about like how to do communication right. This was a smart idea, and it helped to make the project look professional from day one on. So we had a really good logo. We had really like ideas for our channels. We had ideas for the podcasts. It was all like set up. Still, it could have failed. And I think the second thing, which was really unexpected, was how much creative content came from the stops. And that was from the very beginning. We have this fun video of the first professor who from Austria. This was our first stop, where he puts a sticker, and everybody was like, "Oh, you're a movie star! How did we never know you have such great talent in front of camera?"
Better the fun.
So there, as I said, unexpected hidden talents of physicists, which we don't know because they are never put in front of cameras most of the time. Sometimes they are, and I feel Turkey played a huge role in making the project successful because like this challenge really kicked it off. You can see it kick when it suddenly the number of followers increase, and that also, as I said, algorithms makes this more visible. You will like start having more followers. It will go into the feed of more people, and also even before that, every stop was saying like, "Look, we have this European project. It's just something people can relate to. People, even if you're a physicist or not, you've been traveling. Traveling is something you like. You like to explore things. So we had combined this traveling with something physics, so it got a really positive note.
Wow. It is a kind of really long, really fun way to go.
Yes. Can I
I went,
add something
yes, of
to that?
course.
I think I should also mention two things which were crucial to the project's success. So, first of all, we got great support from the German Physical Society, who really made the project possible because they gave us all the organizational structure. And of course, there's also money involved, and we applied for funding via the German Physical Society with the Wilhelm and Else Herios Foundation, and they gave us really also the support. So, in the background, there has been a lot of like organizational things which were running so smoothly, which I'm very grateful for.
Yes. I can say congratulations. Again, congratulations. This is a kind of really, how can I say, big duty to do. I can't imagine that I'm doing that kind of things because it is really big. It is a really kind of a big project. There are lots of collaborators. There are lots of organizations that they're founding, that they're supporting each other, and some kind of an experts, as you mentioned, some kind of a social media and science communicator
Yeah.
experts. This is kind of a really, how can I say, collaborative work, and accomplishment is everyone's, we can say.
It is like I think also you contributed because you're like having this interview with us now. This is great, and you're promoting
Thank
that.
you.
Just coming to the everybody who came to the uh, Izmir Quantum Tech Days. That's amazing. It's like all these support to people. So big thanks goes to all our followers because they are part of the project. It doesn't work when you don't have an audience, does it?
Yes, don't. Don't, of course, doesn't. Maybe we can clapping to our audience, to our followers.
Yes, please.
Thank you for their contribution. Thank you for their support. How can I say? Supporting, we can say.
Yes, yes, this is really it really meant a lot to us. It meant a lot to me. I always have been celebrating every single fellow. Even if they came in the thousands one day, I was like, wow, this is so amazing. It really gives a lot back if you're like doing something and people have a positive response. This is really meaningful to us.
I don't know. I'm just imagining that kind of project of me or our research group or something. It'll be a really good and emotional day when I accomplish that kind of thing. Something we're going to see. Maybe we can get into some kind of a detail of the laboratory experiments. I wonder a lot about that. What
Mhm.
can we do with contoured into the laboratory experiments. It is a really important thing because we have a quantum dot light source.
Mhm.
And it's, how can I say, we are utilizing that for creating that kind of, how can I say, single photons. And the single photon is really important, really crucial for our quantum technology days, maybe we can say
Yes.
for our century. And how we can do that, the contour, it is a little bit weird for me because, how can I say, there's some kind of a torch and we have quantum dot light source and we are traveling that kind of things. But how can I say, it's a little bit dangerous, doesn't it? Because we're traveling the contours. This is a very important suitcase. We can say this is not a suitcase, but contour, we can say, and we are traveling it, and it's a little bit dangerous. How did you trust it to the travel agencies?
Well, I see what you're saying. So let me first of all say, like, the most dangerous is will the torch survive a year of traveling and a year of measurement? Because each stop cools the sample down to 4 Kelvin and then heated it again up to room temperature. They put it on a sample holder into the cryostat. They had and was gluing inside, removing everything, measuring. Sometimes even with just a microscope was involved. So there were different steps involved. I think you can see that very good in the videos that it's like a many-step process. So if many people touch the same thing, the question is, does someone break it?
Oh,
It didn't break. That was really one. I feel like in the beginning of the project we're discussing if we would send more utensils around that. Not only the source, but also maybe some fibers, some coupling, a cooler. That would have been like a large box with much more laboratory equipment. At the end, we decided against that. So it's not something I can do basically at home. That would have been really nice, or like in a lesser equipped lab. So our so the Q torch really had to go in state of the art labs. That was kind of mandatory. But I feel that by doing so, we got a unique behind the scenes look how these labs work. I don't think that like people have an idea how lab life is, or actually have ever been to a physics lab. See if it's very tidy, or maybe it's a little bit messy, or see how many people work there. Sometimes you hear the noises. These labs are really loud. This is very exciting for me. Every time it's like making the noise from the vacuum pumps or from the cryostats. So there's a lot of things going on, a lot of blings, there are lots of mirrors going on. So I feel this behind the scenes look gave also something unique to the Quantum project. And we were not afraid to lose it because it was like a relay race. So every time someone traveled with it. So no, there should be eyes on it all the times. We were not afraid that somebody was going to steal it or like lose it. That was not any concern of us. But yes, it was a concern that it might break, and it didn't. And I think this shows that semiconductor technology is really robust. And we know that semiconductor technology is robust because you have a smartphone, and a smartphone can last for, say, 4 to 6 years, can also last 10 years if you treat it correctly and be really nice. And this shows the quantum light sources based on semiconductor technology will also survive a lot of stuff.
wow. I didn't know that kind of, how can I say, details of it. This is kind of really interesting. How can I say, we take the contour for our laboratory experiments. I didn't know how it become, but it is, how can I say, you said that there is some really distinctive and important conditions to make the measurements happen. Like, well, how can I say, there's a very low temperatures and some kind of a
Yeah.
pressure. We can say, I don't know exactly, but it's something really weird, really fun, really dangerous. And all the things happen at the same time.
I would say danger. It is not as dangerous because we know how to like people who go to the labs. They have a security training that not
Of
like
course.
visitors, but people who handle these things. Something which is an issue even for now. Modern research is. I said we do that all at very very low temperatures. Of course, if we think of a device which will be in our pocket, this shouldn't be at like low temperatures. We want to have that at room temperature. But at the room when we have at room temperature, there are a lot of things which might destroy the quantumness of the states of the physics of the quantum dot or the photons might be not as good as we want to have them. This is why we go to low temperatures. So the question, how can we transition to higher temperatures, is something my colleagues and I are really interested in researching at the moment.
Yes, I can understand it. But I wonder something about this. Didn't you wonder what's going on to the other laboratories at the process of the project or at the process of the laboratory experiments?
And so, what can you rephrase that?
Didn't you wonder what's going to happen? What was going to happen at the laboratory experiments when you, how can I say, sent to the countries, sent to the laboratories, research groups?
Yes and no. First of all, we knew all the groups before, in the sense like there was always like a contact person we already had talked to, and we know what their equipment was and what kind of measurements are those. And the quantum measurements is something which is a very standard. So the experiments they're doing on everyday basis are even more complicated than that. So we didn't propose to them make the most complicated experiment, but we proposed to them make an experiment that should be a routine experiment to use. So I was very trustful. We were very trustful that they will do that correctly, and they will really be able to do it.
Yes, yes, I could understand that.
There was also a very good written documentary by Doris Reiter, who was like the PhD student in the Berlin lab and fabricated the source. He really took great care of writing a very detailed manual.
Wow. We can say what a
It's very impressive.
how can I say, when I search it, this is not the searching, when I follow it onto the Instagram account of you, I was just, how can I say, seeing the other laboratories, other laboratory experiments, and all of the atmosphere of the laboratories, and it was very interesting to see that kind of, how can I say, conditions and labs, and it is like that.
I'm really happy to hear that, because this is what we wanted to convey. We wanted to really show how are the labs, and I'm really happy if someone says, I got a better understanding of it.
Yes, yes, I think so too. So there is a really important question again. I'm wondering that. I'm really curious about that. So what is the long-term goals for the Contour projects? What is your idea about this? What we're going to see into the coming next months, coming next year? Can you please share us?
Sure. So the short-term goal is Christmas break. So this is winter break right now. We're gonna see. As I said, at the moment, the Quantum source is with me in Dortmund. We have the largest Christmas the largest Christmas tree in Dortmund. Let's see if the source can pay it a visit. That would be really cute. But it's going to be winter break. For 2026, we really want to go to more countries. And at the moment, we're targeting Africa. So there will be a couple of events there. We're discussing with colleagues if they can host a source. And it's really showing the global character of physics. This is something we want to convey. And my friend, like Tobias, he always says he wants to visit every continent. I'm not sure how we're going to Antarctica, but I think we can do Australia, Asia, Africa, Europe, and Canada. Sorry, not Canada, North America, South America. So there's a couple of things we want to go. And this is like very, very. I think at some point the source will retire. We're thinking, was yes. We're already like people are already asking, can we have that in this museum or can we have it there? I guess it's gonna stay as a piece of history, not only for the project but also like representing what is possible with a semiconductor light source. So it's a story to tell. Then my colleague says maybe we do Quantour 2.0 with improved source.
This is kind of really I it will be your dreams will come true, I think.
Thank you.
The Contra project is a, how can I say, the greatest project, maybe we can say the greatest project on the world. There's a 10 minutes. Okay, there's no problem with that. The Contra project is one of the greatest projects on the world, I think, as the quantum physics we can say, and I hope, I believe to dreams come soon.
Thank you so much. I'm not sure I can say it's the greatest project, but it's definitely a very connecting project for everybody. I like that a
Yes.
lot.
Maybe we can say that maybe you can start a new project like a contour. This is not a contour, but maybe you can start or think about a new project. It'll work.
Well, let's see. This is what I'm saying. You never know when an inspiration comes. So Quantum was very
Mm,
much inspired because we have like finishing the International Year of Quantum Science and Technology, and this was particularly the spark of initialization for the Quantum project because we want to see quantum physics all around the world in 2025, and I think we did an amazing job. And
yeah.
with we, I mean everybody, all the quantum physicists like had events in wherever. There was a big map on the website, and they show you everywhere popping up small events, and that was fantastic. And this inspired Quantum, and see, maybe there will be another quantum year, or there will be something else we can like go on to and like celebrate quantum even more.
Yes. Thank you for the answer. How can I say? I got really satisfied right now.